All right. Before we get started, I wanted to ask how many people have used EFF before? How many people have used MTL before? Okay. And like reader over IO? Okay. All right. Cool. This, yeah, we're going to be just talking about the very basic intro, some motivation for EFF, as well as, you know, some more concrete step-by-step implementation of how you might introduce something like this into your code base. And maybe if my slides will go. Cool. Yeah, so before we can talk about what EFF is, we need to sort of talk about effects modeling, and I guess more accurately, we need to talk about what problem effects modeling is trying to solve. So there's kind of three motivating use cases that I want to talk about in something that various stories that you may have encountered or that you can relate to in your work that all are at least addressed, if not solved by us, what EFF purports to do. So the first one I want to talk about is requirements thrash, right? It's this idea that, like, a lot of times when we're looking at business logic, the implementation details about what database you're running against, what you know, cache, what you want to do in various exception scenarios, it just kind of doesn't matter to your product managers, right? You're going to gather some requirements. You might want to write out some business logic, but a lot of times you'll have like 70% of your code will thrash on implementation details that might not be related to what your product managers want in the beginning. And so to get cheaper prototypes, we might want to write less code. So in my experience, like, I've had scenarios where I had to like rip out 70% of the code after I wrote it, only to, you know, rewrite it in a different way. And that wasn't, you know, strictly necessary when trying to show an early version of the code to the product managers, and that I could have written a much simpler version that got the point across and gotten agreement and buy-in before, you know, ironing out all of the engineering and implementation details. So the point here is, what if we could write only that 30% now, and, you know, save the other 70% for later after we've kind of got the high-level design figured out and out of the way. So, you know, we want to have this ability to sort of hand wave all the implementation details. Like, I don't really care what it means to save this user off to persistence. I don't really care what it means to go fetch this piece of data from some external domain service. And just assume that we have these capabilities without worrying about how we're actually going to accomplish those things. Another familiar situation I want to describe is that in Haskell, we have an extraordinary type system. And a lot of us might have had the experience that when we compile something, if it actually type checks, then the code will do what we expected and what we wanted to do. Now, this isn't entirely true for anyone who's spent enough time in Haskell. It's like you still get bugs, but entire classes of bugs are eliminated by this. But the stipulation here is that we have, you know, different types of functions in Haskell, ones that are pure, like the one above, sumfunc, right, which takes a foo and a bar and returns a baz, or some other func, which is foo and it does some stuff and eventually it yields a bar. Testing the latter scenario can be tricky. There are a number of ways that you can attempt to do it in I/O. By kind of setting up a test harness that will, you know, in that interface give you back what you want. But by and large, you know, testing the code on the bottom is much, much harder than testing the code on the top. So we also have amazing tools like Quick Check and Hedgehog that can, you know, help us really fuzz the bounds of things like sumfunc, but may be a little bit more tough to use against things that do I/O directly. So it'd be nice if we could, you know, plug and play, you know, various, you know, for instance, logging implementations, and depending on whether we were in our test environment where we can capture all of that to a writer effect and actually test that the logs that we expected to be emitted happened. And then, in our regular server code that we're deploying to production, actually emit those logs to whatever external logging service you have, or to just standard out if that's the way that your log setup is caught. So it'd be really nice if we could basically trap the outputs that our program does and then measure them, supply inputs directly that we could control rather than it fetching it from a source, and then swap out state that might be external to your program to something internal in testing, and then only run these things in I/O when we're ready to deploy to production. Most of our configs live on the same server that is running the code, so we'll have to read that from I/O. Most of the logs are done over I/O, and most of our persistence is done via I/O as well. But we could simulate all of that in testing so that we know that our various business logic methods are executing the way we might expect. So the trick here that we normally do when we want to be able to sort of defer our choice in some design that we have is to make things polymorphic, right? We want to parameterize some type, and that's precisely what we'll be doing here. But the real question is, what are we making polymorphic, right? It's definitely, we might have the function f at the top, right, food IO bar, but we can't make it the middle one because we definitely need it to accept a foo, and we can't make it the bottom one because we know we need to yield a bar. So there's only one real thing here left to parameterize, and this is the monad itself. And I saw a lot of hands go up for having used MTL, so this concept is not particularly new to those of you. But what follows later might. So what we really want to do is we want to parameterize the monad that we're operating in. And so long as it is capable of doing something, that it can really run in any monad at all. Right? Most monad transformers will preserve various actions across the boundaries, like so that you can stack errors on top of states, on top of readers, et cetera. And so we only might need some subset of those capabilities for that particular function. So maybe your business logic needs 1,000 different capabilities, maybe it only needs one. But it's really nice in the case of testing to not have to set up the entire application infrastructure if your particular business logic only needs maybe 2 or 3 effects. So this might sound a lot like mocking dependencies in OOP, and that's because it basically is, right? We want to be able to sort of simulate pieces of code that our code talks to in a stateful way or an effectful way. And then one more thing, just because we're greedy, we want to prove that our function doesn't launch nukes, right? I/O is pretty scary. So you might have something like the top function where you definitely know that f on the top doesn't do any sort of effects because the type signature says I can literally only accept an asset as an input and output a price. And nothing other than the implementation of that function will really decide what that price will be, which is itself more descriptive than the bottom one, which takes a string and returns a double, right? Like that could be any string, and it can return, any particular double. So we use type signatures a lot for this, right? So the question is that given that the top type signature is more descriptive than the bottom one, what is the least descriptive type signature in all of Haskell? IO unit. It's the type of any executable program that you will ever write. And anything, Turing completeness says that anything that a computer can do, a function with that type signature could feasibly do, right? So this sort of reliance that we've grown accustomed to in looking at our type signatures to be able to understand what that code might do completely breaks down when we start to see a type signature like that. It could literally do anything. So it'd be nice to know that we could restrict the types of I/O that we're doing to particular domain effects. We might want to know that this file system function is only going to operate with the file system, and it won't touch the network or the database, et cetera. Versus we might want a network effect that can't do any of the other things in that list. We want to have perhaps a little bit more description around the capabilities that the monad that we're in can do without sacrificing the ability to compose it well with other functions in our program. So to talk about all of this, or to solve all of this, we're really going to talk about a particular construct. This is not by any means the only solution to this problem, but it's one that I happen to like the best. It's quite ergonomic for having solved the 3 issues that we saw before. So EFF is an answer, not necessarily the answer, to those 3 frustrations. And what it allows us to do is we can write business logic and sort of hand-wave the implementation details until another time, because we might be thinking in a very high level, and then we can go deal with the gritty details at another time. We can swap out implementations the same way that we wanted to for our testing by just swapping out our interpretations. And we can very specifically mention the capabilities that we want this monad to have. So the question is, how do we do this? What we're really trying to do here is we're trying to sort of bisect our code base into a what we are doing and a how we are doing it. And largely keeping those not only separate, maybe logically, but literally putting them in separate files if we want. And the business logic is something that your PMs might care a lot about, and they don't care pretty much anything about how it works. And the execution environment does still care about how it works. So we won't be able to avoid that entirely, but we can separate it and clean things up, as well as defer it to a later time. So what libraries will help me do this? Well, the one that I've been using most recently is Freer-simple. There are a few other ones. I can't really comment on whether they are better or worse, so use at your own discretion. But I can, I guess, personally attest to the fact that Freer-simple is nice to use and works well enough in production. But I also want to point out this one on the bottom, Polysemy. It's a very, very new implementation by Sandy McGuire, and it's one of the things that we'll talk about later is that Freer-simple can incur a non-trivial performance cost. And Polysemy fixes some of that. So what's a minimum viable EFF effect? Like what is this thing that I've been talking about up until now? And the idea is that we want to think about these operations that we're doing in very contained manners. And we'll define a data structure that represents that effect. And then we'll interpret that data structure with a function later. So the sort of belabored example that you'll see in pretty much all of the literature on this subject is the console effect. And this is the idea that, I'm sure many of you, when you learned to program, probably did some sort of CLI tool that asked for input from the user, and you type in the input, and then it will print out to the console. It's just sort of two-way communication channel with the user. So we can represent that here. So I'm not going to explain GADTs in detail, but you will need to turn that extension on to use this sort of thing. But the idea is that we'll define this data type in this special syntax that you may or may not have seen before. And for any sort of, I want to say reader effect, you're going to just create a data type with no inputs. And then any sort of output effect, you might have an input and then unit as the sort of free variable in the console. And then you might have, in other scenarios, state, which we can talk about later. But the idea here is we've defined as data the operations that we want to do. And we're going to use some template Haskell magic to do some stuff, which I'll explain on the next slide. But this basically, in this particular case, it will define a way to get something from the console and a way to put a string to the console. So as I said, the make effect generates a couple of definitions for us. You might ask, why didn't we just write these ourselves? And for a two function algebra, that might not be a lot of work, but sometimes these things can get significantly larger. And so it's nice that the very mechanical process of defining these lowercase functions get written for us. So all this does is take this data structure that we defined on this slide and basically injects it into this EFF machinery, which I'm not really going to talk about how it works under the hood. Just that it is a monad that is capable of basically jamming a bunch of effects together in no particular order, such that you can sort of grab capabilities at will and then have the interpretations decide what specific effects are going to be there. So in this case, getLine is an action in some polymorphic monad, EFF, that so long as it has the console capability, it will yield a string. And then putLine is a function that takes a string and returns an action that will yield unit so long as it has the console capability. So, morally similar to, monad state, monad reader, monad IO, it's this polymorphic, monad that just requires a specific capability. So with that, we can write our business logic. We actually need to say nothing about how we're going to go and deal with those interpretations. And we can just write, some sort of trivial bot that will repeatedly ask for your name and then greet you forever. But we haven't specified anything about putLine and getLine yet. So we've separated these things out, and maybe skeptics among you might say, well, hey, base already exports getLine and putLine, and I didn't have to inline those definitions into this anyway. So why did we go through this exercise? And the answer is that we haven't even committed to what those implementations are at this time, right? Whereas the definitions in base might have a very specific implementation. So now that we've done that, now that we've written out the business logic, Freer doesn't really save us from having to write the implementations. We can just do it in a different place. So we might write the real interpretation that we want to run in our program, because at the end of the day, we can't escape running these things in I/O. But we can just avoid committing to them. So we do still need to write this interpreter. And as you might expect, we just simply take that data structure that we defined, and we case on which one it could be. And in the first case, where it's getLine, where we just use the getLine from base. And in the case of putLine, we grab s and we feed s to the putstrlen from base. And with that, actually, we have enough to be able to run this thing as just a program. So a brief aside, Freer Simple exports a lot of combinators for being able to compose these interpreters. And so a quick one that we'll talk about, we'll notice here that the type signature is console A to IO A. So morally speaking, this is a natural transformation, but the idea is we're just trying to do a very simple transformation between one data structure into another monad. And so translate gives us the ability that so long as we have a way to go from FA to GA, we can do that same transformation when all of it's happening in the EFF machinery. Run-M discharges all of the EFF machinery if there's only one monad in the list. I just realized one of the things that polymorphic R that you see here is a type level list, right? So like I said, we jam a bunch of effects together in this sort of type level list, and we sort of interpret out those effects one by one until all we have is one. And then this run-M sort of sheds all of that, and we're back into the regular monad that we might have used. Yes?
On the previous, I think 2 slides ago, you had this member constraint.
Yes.
Is that coming from EFF, or is that coming from type level lists?
So type level lists in general are not defined inside of any of the Freer libraries. They are something that is a consequence of the data kinds extension. The member console constraint, the member AB constraint is coming from Freer. So that is not something that you will find outside of Freer, but you might you might be able to define it and make use of it in other cases. It is literally just a type level membership constraint, not strictly useful for EFF. So if we want to then take that console A to IO A that we wrote on this slide and be able to actually operate on it in the EFF context, we kind of use runm and translate together. And I'll leave it to you guys to work out the types on that. But the idea is that we're translating console to IO, and then we're going to discharge the EFF machinery. And then our main would look like that interpreter on the greetbot business logic. All right, so what about testing? I promised testing. So first thing we need to do is actually make a small refactor of greetbot. The issue is that things that run forever aren't really good to try to test. So we'll, instead of having it being infinitely recursive, we're going to sort of factor out the recursive call. And I think used a keyword that I should not have. So don't actually try that with the actual like a rec value. That will not compile, most likely. But anyway, any other parameter there would do. And basically use the fixed combinator, which if you haven't used it before is just a way to turn things that don't have explicit recursion into recursive calls. And what we're going to end up testing here is greetbot prime and not greetbot, because forever stuff is really impossible to test. So I use Hedgehog a lot, but all of these Hedgehog examples are portable to QuickCheck if you guys use QuickCheck. But the idea is that every time you see one of those for all something generators, you can think of that as arbitrary in the QuickCheck setup. So we have a name that we want to feed to this thing, right? But we need to figure out how we're going to get greetbot to accept it, right? So we need controllable interpretations. We need to be able to sort of control the inputs and measure the outputs. And so, in this scenario, if you think about it, this is really just one reader effect and another writer effect, right? So armed with that, we can decide, well, in the getLine case, we might want to ask the environment in the sense of reader. And in the putLine sense, we want to just emit it to our writer effect. Now, in the case of Freer simple, it ships with a bunch of effects basically right out the gate that you don't have to define yourself. Reader and writer and state and all of the typical transformer library stuff can be found in that package. You can redefine them yourself as an exercise, but it's not strictly necessary. But you'll notice here that the type signature for console to reader and writer looks different than the one here where it's just console A to IO A. And that is because the only way that we can really compose these things is by putting it into the EFF machinery. So we will need a few different combinators that are coming from the Freer simple to actually make use of this particular interpretation. So let's look at some combinators. Reinterpret and that family of functions basically says if we can take one effect and turn it into some coproduct of effects, whose cardinality is that number that you see on the side of Reinterpret, that we can do that inside of the EFF machinery. So you'll notice here we went from console A to EFF RA, where it has two different things that it needs. So we'll use Reinterpret 2 to make sure that we can do it inside of EFF. Additionally, Runreader and Runwriter do similar things that they do for transformers. And you can supply the actual reader input. And for Runwriter, you also get a W as the output. And then run, in this case, basically says if your effect list is empty, as in there are no effects, we can just shed all of that machinery and get a pure value out because there are no effects left to interpret. So closing the gap, we can compose all of these interpreters together. So the Reinterpret 2, basically taking the one console effect and turning it into reader and writer, and then handling those effects individually, and then run to discharge all of the machinery. And then we get a function that looks like that, which if you've tested Haskell code before, that's a really happy function to test. So yeah, pure values are great. We should strive to do them as much as we can. So before we didn't know what to put there, but now that we're armed with that particular interpreter, we can go about doing this just fine, where instead of the recursive call to greetbot, we just put a pure unit, basically say we're gonna test one iteration of this and that's it. We grab our arbitrary name from our generator and feed that into the reader, and then we measure out the output of the writer effect. So obviously, if it doesn't actually greet us back and emit something to the writer, then we want to fail that test. And if it does, we want to make sure that we want to measure something about the log that got emitted. All right, so what have we done so far? We've defined a new effect called console. We wrote a real implementation in I/O. We wrote a test implementation that was good with our test harness. And we explicitly stated all of the capabilities that we needed in our business logic. So hopefully we can see that that particular implementation gave us the three, or at least flexibility on the three different things we had set out to in the beginning. So can we do this to everything? The short answer is yes, but some things are more valuable than others, right? And the rule of thumb that I've sort of come around to, and I'm still learning a lot of this stuff, so I can't necessarily teach you judgment in a 50-minute session. I don't think anyone could. But the things that I've figured out so far is if your API has well-defined semantics, or if you need to mock it, they're probably good candidates for this sort of an implementation. In every other case, there's some really interesting things you can do with this, kind of if you're really pushing the edge. But in a lot of cases, in a business environment, you might lose more than you gain from other cases like this. So we did the belabored example that is in all the literature, and I want to do a little bit more of a real-life example because unless you're just learning to program right now, most of you probably will never actually write a console greeter ever at work. So the problem statement that we're going to use is we're going to fetch prices from a third-party API. We're going to save them to some storage, and then we're going to serve the most recent price upon request. I work in cryptocurrency, so a lot of this is because of that. That's what this example is about. So let's write a new effect algebra. First of all, we have this feed where, given an exchange and a pairing, we're going to have some effect that yields a price. As far as I can tell, that's the only thing that we need for that particular algebra. The types of asset pairing, price, and exchange are totally not important for this example. And then we might have something like a persistence, right, where we want to save it and we want to retrieve it from that persistence. So we have a price store, which given a pairing and a price, we can save and then look it up by pairing and get the most recent one. So again, now that we have gone through just the effect algebras with the make effects, we can write the business logic entirely just from that. So for every exchange, if we have many different exchanges, we're going to go fetch it. And then our fetch and save basically gets it from all sources. It does some aggregation, and then it saves that price to the store. Everybody following so far? Cool. So if you guys write Yesod applications, then you probably need to wire this into an actual handler. And the real question is, what goes in those question marks, right? We know how to get the most recent one because we basically told ourselves that we were going to have that capability somewhere. I had it here somewhere. Yeah, OK, that's right. Duh. Sometimes template Haskell can hide some of your definitions. Yeah, so we get the most recent price, and we need to convert it to JSON because that's what everybody does for APIs these days. And we don't know how to wire it into handlers right now. So somehow we need to go from our price feed to our handler value. And so that says, let's make an interpreter. So some other things about the free or simple, what you'll notice a lot of times is that in this case of the for all A, FA to GA, A is somewhat not important to this. What we really care about are F and G, this transformation between the way that we're representing something. So a lot of times we'll use this sort of squiggle arrow function, which is unfortunately quite overloaded depending on how many different packages you have in scope. And then we might have some external source that has an API key that it requires. GDAX actually doesn't, but I'm making this up for the purposes of teaching, so we're going to pretend it does. And then we need a way to convert it to extract out the raw response to just the piece of information that we want. Asks is probably a familiar function to anybody who has used transformers before, but the idea is you just implicitly are also applying a function to whatever you're asking out of the environment. And it sort of smashes together this sort of monad ask and then whatever function you would nominally fmap over it. So an interpreter into reader over IO will look like this transformation between price feed and EFFs, where as long as we can read out the exchange configuration and as long as we can do IO somewhere in there, or really at the bottom, then we can do the rest of this. So we might ask to get the GDAX API key out of our environment, do some regular old IO code from HTTP, and extract out the result. This part should seem relatively familiar. This might be code that you would write if you were just writing directly into IO. But what do we want to test with? We can hit real exchanges now, but do we want to do that inside our CI pipeline when we're doing continuous integration and shipping out new artifacts, if and only if they get their tests to pass? My experience is that this is not a good idea, A, because it's slow. HTTP requests are probably the slowest part of your entire application. And if you're operating your CI inside of a private subnetwork, you could have all sorts of weird firewall rules that your security team has set up that prevent you from doing this from those machines. Plus, we don't need to because we're not really testing the reliability of those particular exchanges in that function. We want to just test what that function is doing. So we realize that because we're really just asking for information, whether we ask for it from the environment or we ask for it from an external domain service, it's really just this notion of a reader effect. So we can transform it exactly to a reader effect. Don't give me shit for putting from just here. It's a conference talk, and it's a test interpreter. So yeah. In the case of a price store, we have a little bit more complicated of a relationship going on here. It's not just a reader effect that we might be wanting to do. in real life. But it's reasonably the case that you might want to save these things to Postgres, right? So we could just ask for the pool, out of our, Postgres, you might have a connection pool that is managing all of your connections, and then we need to do I/O. So this might look, again, like a little bit of a reader I/O effect. That's a common pattern. So we can, after we have the connection pool, then we can just use or call the persistent functions. I'm doing a lot of this from the Yesod persistent opinion. Hopefully you guys have seen some of that before. If you haven't, please ask. Yeah, but insert for save, select first for get. The actual implementations I'll leave as an exercise to you. But what if we don't want to save it inside of just Postgres? We want to save it inside of a cache instead. Turns out that because we didn't commit in the business logic, we can do that here. And so we just need to ask for the cache, save it to the cache using some sort of STM implementation. And then during the gets, we just read those things back out. But what's really interesting about all this is that since interpreters are reusable, we actually can write a third interpreter in terms of both, right? Where we might want to save both to a cache and a Postgres for historical purposes. But realistically speaking, most of the time we're going to be fetching this, the most recent one in real time anyway, and that doesn't necessarily need to come from disk. So we might want to have this sort of low latency cache in addition to our persistence. So rather than write a new interpreter entirely, I can actually reuse these two in here. So you'll notice price store to Postgres on the action, and then price store to price cache on the action for save, because we want to save it to both locations. But because we want to go pretty fast, and there's no need to fetch it out of the database if it's in our cache, we'll just grab it from our cache. Now on startup, you might want to populate your cache with the most recent one from persistence. But that's more of a kind of engineering decision. So now that we have now that we're equipped with those things, we actually have the ability to put the stuff in the question marks that we had before. So if we use our handy Reinterpret 2 that we talked about earlier in the talk, and we basically use the Postgres and cache option, then we also need to handle the various reader effects, because we need to have a reader for our cache, which might be inside of our app object. And we might want to, and we still need to handle the fact that we need a connection pool, which is usually also stored inside of your app type. And then finally, because a handler is a monad IO, we'll just go ahead and do a quick lift IO and get Yesod to actually get that app to feed to the other things. So this is our entire interpreter that we would use in the actual get price. And you can put interp where those question marks go. So what's the catch of all this? Like, why wouldn't you do all of this? The answer might be that monadic binds are roughly, I think I've heard reports between 20 and 35 times slower. First of all, that sounds like a lot. But second of all, it's still faster than most interpreted languages. So if you've ever deployed a Python web service and felt like that performed OK, this is not going to hurt more than that. But secondly, it's also not that your whole code is slower. It's just in the binds, right? And then there's obviously more setup and sort of like a little bit more boilerplate to get all these than you would in the case of just doing everything straight in I/O. But the polysemy implementation fixes the speed. And one more thing. Resource bracketing and other non-algebraic effects cannot be really well expressed by free or simple in particular. But the experimentally new polysemy library does actually do not only a fast implementation of the first order effects, but also higher order effects such as resource bracketing. So to wrap up, Freer-monads can make your code more testable, better documented via the type system, and in some ways can make it more orthogonal by not conflating the what you're doing with the how you are accomplishing it. And it isn't the only technique that accomplishes this. Any of you that have used MTL probably know that this is something that you've been able to do in the past. And this is, in my opinion, more ergonomic, but still accomplishes all those same things. So I'd encourage you to at least consider something if you have experienced any of the 3 pain points that I mentioned at the beginning. Yes?
Pure script seems to be taking effects in kind of different directions from Haskell. Can you make some comments about your feeling on are they right through wrong truth or whatever?
So I will first caveat this with I have never actually written pure script code. But my understanding of this problem is that the original pure script implementation used row types to handle the effects. And most of the problems with that came up with trying to get the row types to line up. I believe there's like a pure script effect versus pure script run or something like that. Anyway, there are 2 different EFF implementations in pure script, and this more accurately corresponds to the one that does not ship natively with pure script. So I can't really comment on whether I think PureScript is doing a good thing with the direction they're heading with this or not, because I'm just not a PureScript programmer. But I know that there are some in the audience. So if you want to comment, if you want to track one of them down and ask them about that, I think that someone else could be a better person to answer that.
What was the significance in declaring that IO is the last member of the EFF stack?
Yeah. So that's not strictly necessary, but it does have the added benefit of type inference. So one of the things that you might lose, if you've used MTL before, you've probably run into the constraint where you can only have one monad state or one monad reader effect in your stack. And that's because there is a functional dependencies constraint in those type classes. And the reason that Kmet put those there is to aid in type inference. And one of the reasons we use Haskell to begin with is because we don't have to annotate types everywhere to be able to write code that we get a lot of type safety out of. Now, Freer, as a sort of principle, eschews the idea of only limiting yourself to one reader or one state or whatever effect, mostly because sometimes you just want different ones. You might have certain things that have a reader on one config, or if you have like one helicarrier config, you might have sub-configurations that some of your functions only need some subset of your config. And you otherwise would not really be able to express that in MTL. There is like an MTL unleashed library that sort of does the same thing, that eschews that functional dependency, which gives you these more effects. So by sort of eschewing this limitation, though, we kind of lose some type inference, right? If you are doing an ask and you have more than one reader in your stack, then you might not know which one it's referring to. And in the case of the last member, it's basically anchoring the type system to be able to say, like, all right, I'm looking for IO not only somewhere in this list, but like in particular in the last place. And it's purely to help your compiler. There are differences of opinion as to whether this is or not this is a good idea. In those places where I did last member IO, I could have done just regular member IO, and it probably would have worked. But I have not seen a reason not to do this up until now.
You have last member IO, does that mean you can no longer test it the way without IO the way you wanted it?
If your interpreter interprets into something where you have last member IO, then yes, that is the case.
It's just the interpreter, right?
Correct.
So the effect functions, they didn't have anything to do with IO. It's just the interpreter.
Correct.
Okay, so you just didn't display an example of like maybe an interpreter that you use in a
Not in the most in the last example with the store. With the feed, I think I did, but yeah, there are a lot of cases where you might want to do stuff like this, but there are situations where you could do IO as not your last member. I have seen people try to do IO as a regular member and then try to catch all of the IO exceptions and interpret IO into some sort of like safe IO where it like interprets it into like some errors and then IO again. But yeah, most of the time I've seen it, it's been in the last position. Same way that you might see it in monad transformer stacks.
Is this compatible with Real library?
So I haven't used the Real library. As I understand, it's fairly new. I'm certain that it can be hacked to be compatible. And the reason that I believe this is the case is because I currently use a hacked version of Protolude with this in it, where I hide all of the transformers imports and I pull in all of the Freer effects imports in their place. And so that roughly, and I've gotten a lot of mileage out of that pattern. So without knowing too much more about the implementation details of Rio, I'm not sure. But I mean, you'll have to do a little bit of hacking to get them to play nicely, but not anything that would like have you tear your hair out. It's just a little bit of boilerplate with your prelude. Yeah. But I mean, I don't know why I would make Rio itself a combined effect when I could just separate them out. I think the real value of Rio is to have a single monomorphic monad that encapsulates both of those effects, just the reader and the I/O, and then not having to deal with the polymorphism throughout the rest of your application. So I don't know how much sense, I think you can do it, I just don't know how much sense it would make.
There's a lot of other things in the Real library besides that, so I guess you can go ahead and use it.
Yeah, certainly. Yep.
What is resource bracketing?
Yeah, so there's this idea that in any sort of code that has to make use of a finite set of resources like semaphores or, you know, in this case, connection pools. It's most often in connections pools like your HTTP manager and your you know, database connection manager. There's some finite set of connections that you have established to your database. Like if you have a concurrent set of web server calls, you don't want to just keep opening connections to the database, and you want connection reuse wherever possible. So you have this issue where you have this, this finite set of resources, and they all need to sort of take turns grabbing things out, and then when they're done, returning them to the pool. So what resource bracketing allows you to do is basically say, all right, I'm going to assume that I have this thing, and then use the resource bracketing to basically allocate at the beginning, give it to you inside some block that you need it in, and then when the block is finished, it returns it to the pool, and even if in the presence of an exception.
Okay, so you mean like the bracket function?
Yes, exactly. So, yeah. Interesting other uses of resource bracketing can be database transactions. I have actually done that in terms of bracket as well, where rather than having a resource that actually gives you in the block, you can actually mute that particular argument and basically have it accept nothing. But it basically allocates by starting a transaction, ends by ending a transaction, and in the presence of an exception, will roll it back.
And then you're just saying that's like a bit difficult or not able to be encoded in this type of thing.
It's not in free or simple, but it is, and the reason for that is that my knowledge on this is a little thin right now, but my best understanding is that it requires embedding effects one layer deeper, because you have the thing that requires the resources, the place where the resources in the effect stack, but also you're embedding an action within that, and so it needs to sort of persist through that, and that's a very complicated type system thing that was only recently just solved. Like, and when I say recently, I mean like probably in the last 4 weeks. Yeah. Sweet. All right, I'll be around for the next hour.